welcome to Friday's edition of Cracking the Cryptic, where today we see the return of SudokuExplorer to the channel. SudokuExplorer is an exceptionally good constructor. I was looking at the ratings of their puzzles on Logic Masters Germany just before I started the webcam, and literally every puzzle they do is sort of very well 95% rated. Extraordinary beauty levels. You look through the comments and they're just to die for. A seriously interesting constructor who always comes up with novel stuff. This one's called Trapped by a Killer, and as far as I can tell, quick glance at the rules suggests to me this is a normal killer Sudoku. So I don't know how hard this is, but it should be very interesting, because actually it's quite hard to get on the channel nowadays with just a normal killer Sudoku, because we receive so many puzzles. And they tend, the puzzles that tend to make the grade now with our testers often combine different rules. So I'm looking forward to trying this. Do I have anything else to mention? Not really today. We've obviously got the new reward over on Patreon, so if you're a patron of the channel, go and check that out. People are already enjoying that. Something a bit different this month, where basically there's a Mexican standoff between 3 different setters going on, and you have to work out who wins. So that's all I've got to tell you. Let's have a look at the puzzle. I'll read you the rules. We've got normal Sudoku rules apply. In cages, digits must sum to the small clue in the top left corner of the cage, and digits cannot repeat within a cage. So completely standard killer Sudoku. So those 5 cells there add up to 29, and we can't repeat a digit. So we can't, for example, try and do that, because although these 9s don't see each other, using normal Sudoku rules, they are in the same cage, and that's not allowed in killer Sudoku. Do have a go at the puzzle. The way to play, of course, is to click the link under the video as usual. Now I get to play. Let's get cracking. Okay, so there is very little to get my teeth into, I think, in this grid. 17 in 5 cells is a bit restricted. It's got to contain a 1, 2 and a 3, and then 2 of the digits, either 4 and 7 to make the extra 11 that we need, or 5 and 6. So it's probably something to do with these 17 cages. Let me just have a think about this. 21 doesn't have to have a 9 in it. It could be 6, 7, 8. 29 would be lovely if there was 1 cell less in it, because then it would be 5, 7, 8, 9. But once you introduce a whole extra cell, all of the tension sort of drops out of the cage, and that, I mean, this is nothing. 14s, 18s, a 22. This is already feeling very strange to me, actually, that this has a solution. It obviously will have, because, well, I don't remember the last time I opened a puzzle and found that the testers have put it into the software wrong, but it is puzzles like this that make you wonder. So what's going on with these 17 cages? Let me just highlight them and let's have a think. So yeah, I mean, what I'm wondering is it's such a small thing, but, you know, for example, can you rule out 1, 2 and 3 from being in those squares? I don't think you can. I don't think that you can. There's still too much flexibility. Can you rule out 1, 2, 3 from there again? It's weird. You've got these chevrons of cells. These are all very high digits on average. The average Sudoku digit is obviously a 5. So this is averaging 6.66 recurring. This is averaging 7. That's averaging 6. That's averaging low, though. That's averaging over 7. Oh, hang on, what am I talking about? That's not averaging over 7. I was thinking it had a different number of cells to the number of cells it actually has in it. No. Deliberate mistake, just checking you were concentrating. No, I mean, it's averaging over 5, but still averaging less than 6, so it's a pretty average cage. Good grief, what's going on here? It's probably set related in terms of, by which I mean there's going to be some geometric trick in this grid that we're going to have to spot. But I have to say that normally I get quite a good sense for where the set's likely to be. I mean, the first thing I'm seeing is possibly something like the Aard van der Wetering trick, which equates those 16 cells with, well, these cells on the other side. Let's just highlight those in a different colour. But here that looks awful, because there's so much real estate that's uncovered by cages. I think that's absolute nonsense, to be honest. The next thing I'm thinking is it these T pentominoes somehow? I don't like the look of it, though. No, I don't like the look of it. I mean, these sort of the pentominoes that I've just highlighted are suggesting some sort of lattice, aren't they? Like this shape. But I don't like the look of that, really. It looks like it's turning the puzzle into a Windoku. But there's still an enormous amount of the puzzle there that I don't think is going to overlap in terms of the cages. So I don't like the look of that. I don't like the look of anything. I really don't. I don't know what on earth am I meant to do here. It must be the 17 cages. Let's have another think about these. So, can we prove these are different, for example? Maybe that's what we've got to do. I.e., if one of them is 1, 2, 3, 5, 6, perhaps the other one has to be 1, 2, 3, 4, 7. So if these were the same, exactly identical compositions, then there's just no pressure. There is no pressure. There's no... I don't understand. Oh no, this is a disaster. This is an absolute disaster. This is one of those videos where I think I'm going to conclude quite quickly that I can't do it. It just doesn't... There's just nothing here. Let me just think. So what else could we do? Fistemafel type things? They just don't look... Oh, Fistemafel, maybe the 2x2s. Maybe I'll just have a quick check of this one. So I'm thinking of this sort of slightly inwardly flexed Fistemafel ring, which is those 2x2s, which equate, if my memory takes me, or my memory serves me correctly, to these cells. So let's just take a quick stare at this. That's just not as point. That's absolute nonsense, isn't it? Even though some of these 2x2s are well covered by the blue squares, there's still a whole 2x2 there uncovered, along with this cell. No, another load of nonsense from Simon. Oh dear. It's not this 29. I keep looking at this 4x4 and thinking there's something going on there. What is it I'm meant to appreciate about the geometry of this puzzle? I just don't know. It might be some sort of weird subset trick. So I take those and those. What I'm trying to do is I'm trying to map the cages as much as possible onto something that looks sensible. Again, what that one seems to... Again, I don't keep coming back to it, but this L-shaped region here, it's sort of pointing you in that direction. But then how do we split this up so that it actually means something to us? Let's highlight that. I quite like the fact it leaves Windokus behind, but I hate the fact that this area is completely uncovered. This area is completely uncovered. So, the other thing we could do actually here. What I was thinking is I was going to have to split up this lattice I've drawn. So I was thinking that I was going to sort of maybe try and remove or make this one colour, maybe make the rows one colour and make the columns another colour. But if I actually keep the whole of this area as orange, although I really don't like that either because that's going to lead to double squares. But I can see how if I now highlight, for example, if I highlight box 1 in a different colour here, I actually get rid of a lot of uncaged cells. Let's just have a quick look at that. So actually, hang on, before I do that, let me just count what I've got here. In orange, if we go with this set arrangement, the orange cells, if I count all of the overlaps twice, it's 6. 1, 2, 3, 4, 5. It's 6 complete sets of the digits 1 to 9 if I count these overlap cells twice. So I've now, if I allocate a whole blue box here, I've got 6 orange versus 1 blue, but I can get rid of those cells. Yeah, okay, I'm going to do the same in that box because that's just going to leave caged cells behind. So if I make this whole box blue as well, I'd get rid of those. So now I've got 6 orange versus 2 blue, although I've got to remember these two are still orange, aren't they? Because I can't cancel them down. I think what I'll do is I'll keep talking and jabbering. If this looks likely, I'll go through it more slowly. Yeah, the central box looks quite good actually. Maybe this is right. But I still don't know what the overall sets are, so let's just carry on with this. So those would come out. Yeah, okay. Okay, this is, I'm now thinking this is right. Because I keep being able to find overlapping cells that are not in cages and leave basically cage cells behind. So at the moment I've done 1, 2, 3, 4. I've got 2 more. I'm going to do that one because that's going to get rid of a whole load of stuff as well. I'm not going to do box 8 because box 8's already perfect. So yeah, we do this one and we get rid of those. And now, yes, and now I do box 9, which I think is then I've highlighted 6 whole boxes in blue. Yeah, but I was thinking, I don't look like I've got the same number of cells, but that's because, of course, I've missed out all of the corners. But this is definitely interesting, right? So we're gonna revert, and we're gonna do this slowly. So what I'm thinking is, I'm gonna highlight 3 rows of this puzzle in orange, and I now can say absolutely precisely what's in these 3. What's in the orange cells? The orange cells must be 3 sets of the digits 1 to 9, because in each complete correct row of a Sudoku, you get the digits 1 to 9 once each. So this is 3 sets of the digits 1 to 9. But I want to add more cells into my orange set. But before I do that, I want to imagine that I get a set of Scrabble tiles. So I've got 27 Scrabble tiles. And on each of the Scrabble tiles, I write one of these digits. So I find out what digit is in here, and I write it on a Scrabble tile. I find out the digit in there, I write it on a Scrabble tile. And I'm going to put all 27 of those Scrabble tiles in a bag in this hand. Okay? But I'm going to keep going. I'm going to highlight this whole column again. And I'm going to do it exactly the same again. So I'm going to write this number on a Scrabble tile, this number, etc. Now you can see this one was on a Scrabble tile relating to the row, and I'm now putting it in again because it's in this column again. So I've now upped the number of Scrabble tiles I've got to 36 Scrabble tiles, but these three digits are effectively repeated. Hopefully that's clear. Maybe I'll make that a different colour. Sorry, I'm just trying to make it clear which are the double counted digits. I'll give them a black flash, and I want to add this set of digits 1 to 9. So the whole of column 5. So again, I'm going to write each of these digits on a Scrabble tile, another 9 Scrabble tiles, pile them into my bag of orange. Obviously these 3 digits have therefore appeared on 2 Scrabble tiles. Do the same in column 9. These 3 digits are going to appear on 2 Scrabble tiles. So I've now got 6 times 9 equals 54 digits in this bag. And I know that these 54 digits are exactly equal to 6 whole sets of the digits 1 to 9, i.e. there will be 6 number 1s, 6 number 2s, 6 number 3s, etc., all the way up to 6 number 9s in my bag. Now I'm going to highlight a different 6 sets of the digits 1 to 9. I'm going to highlight the whole of box 1 in blue, so you can see that the whole of box 1 is obviously a set of the digits 1 to 9. I'm going to write each of those digits on a blue Scrabble tile and put it in a blue bag here. And I'm going to do the same for this one. And I'm going to do this. So that's another set of the digits 1 to 9. I'm going to do the same for this one, this one, this one, and this one. That's another. So altogether, that's 6 sets of the digits 1 to 9 in blue. For every one of these digits, for example this one, I'll write it on a Scrabble tile and put it in a blue bag. So at this point, I've definitely got 6 sets of the digits 1 to 9 in my orange bag and 6 sets of the digits 1 to 9 in my blue bag. Now I'm going to find cells like this. Let's say that this digit was a 6. I'm going to go and hunt in my orange bag for the 6 and throw it away. And I'm going to hunt in my blue bag for a 6 and throw it away, because I know that if this digit is in both bags, if I remove it from both bags still contain the same contents. They just contain one less Scrabble tile, but they still have exactly the same things in them. So I can do that for every single cell in this puzzle that is coloured both blue and orange. I'm going to ignore the ones with the black flashes at the moment. We'll come back to those. Bang, 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 bang. I think that's all of them, but I'm not sure. Let's just have a quick scan. I think that looks good. Now, I just want to think about this one. What we know about this one. We know that this is in the orange bag twice, but in the blue bag once. So if I take one of the Scrabble tiles out of the orange bag, for whatever this digit is, and one of them out of the blue bag, I'll be just left with this digit in the orange bag once then. So every single time we get this going on, this is different. Every time we get the blue and orange and black, we know that the net result, in order to keep the bags the same, is that we need to leave one orange in each of those. Now this one, and this one are complicated because they are still in my orange bag twice, but they were never in the blue bag at all. So at this point, we should have the same number of digits in blue and orange, remembering we've got to count these double. So let's just check that we're not already wrong. 5, 6, 7, 12, 13, 14, 15, 16. Oh, hang on, I didn't count them twice, did I? What am I doing? Okay, let's do that again, but this time, so I'll just count them once, and then I'll double up these double ones at the end. So 5, 6, 7, 12, 13, 14, 15, 16, 21, but I've got to count this again, and this again. 24 digits are in orange. Now we should have 24 digits in blue. So we've got 7 there, 12, not sure about this, 19, 20, 24. Yeah, we have. Good. So now what I'm hoping is that there is some restriction, because we know that the blue digits at this point, the digits in my blue bag of Scrabble tiles, are identical to the digits in my orange bag of Scrabble tiles. So, for example, we very nearly know what the orange Scrabble tiles add up to. And that's because we very nearly know what the blue Scrabble tiles add up to. It's only 4 cells, look, that are not caged in blue. We also know, and this is probably more interesting, we also know that in orange we have 2 1s, 2 2s and 2 3s, because there's a 1, 2 and a 3 in that cage and a 1, 2 and a 3 in that cage. So there must be 2 1s, 2 2s and 2 3s in blue, which is almost interesting. You can't put 1, 2 or 3 in the 21 cages. No, there's still quite a lot of flexibility actually. Let's add them up. So, what have we got here? We have got 50, 64, 85, 103, 123 in blue, plus these digits. 123. Now, does that feel high or low? That feels high. My phone's buzzing at me. So, if that's high, we should be thinking about, is it possible to get 123 plus 4 more digits for whatever these 4 are? So if I'm right and blue is a high number, we need to minimize these numbers. Okay, what's the absolute minimum I could put in there? I could put 1s in those 3 and a 2 here. So the absolute minimum, I think, that I could put into the blue squares, that would be another 5 on top of my 123, is 128. So is that remotely difficult to achieve in the orange? 128. I've got 34, 36, I've got 56 at the moment. What do I have to get to? 128. That does actually feel quite hard. 44, 72. That does actually feel quite difficult, doesn't it? 34. Oh, I was just thinking about this. How on earth am I going to make this work? Because I'm forgetting I've got to double these again. Ah! So I was adding these up and going, well, that's 17, and that's 22, but that's not correct, because of course whatever sits in these digits could, it doesn't could, there's no could about it. It must be doubled. So actually the oranges add up, so this cage adds up to more than 17 is the key point for the purposes of this calculation, because whatever goes in that square is repeated in orange, so counts twice. So maybe a better way of doing this is actually going to be to write in the maximum I could put into those squares are 8s and 9s. So that would give me 51 in these squares for sure. So we've got 51, 68, I'm going to do the doubling again at the end, 68, 85, 87, 100 and, what's that, 107, 107, yes, that's it, that's it. So the maximum I can put, this is ridiculous, the maximum you can put in, if I absolutely max these out, I can get and count everything singly. I can get to 107 in orange, but I need to get to at least 128. Well, the only way of getting to 128 is going to be to add on another 21 in these cells. But look at this 8-9 pair here. There's no way this square can be bigger than 7. There's no way this square can be bigger than 7 because it's in a 17 cage. If I make this an 8 or a 9, well, it can't be an 8 or a 9 anyway because of the 8, 9 I'm guessing might be in the column. But if there was an 8 or a 9 in here, you couldn't make the other 4 digits add up to a small enough number because 4 digits, if they're different, must be a 1, 2, 3, 4, at least 10. So there is no 8 or 9 in there. So there's only one way this can possibly work. It's actually a weird geometric trick. We've got to put 7s in those 3 squares. We've got to have 8, 9s in everything else I've put 8s and 9s into. We've got to minimise these, which was... How did I do that? I put 1s into all 3 of those and then a 2. This 2 obviously sees these 1s. We can't, if you do it the other way round, you're going to have too many because you're going to lose a degree of freedom. If you put 1 here, those 2 obviously have to go up and that removes. So those 3 add up to 5 now, whereas we can, if we minimise them, make them add up to 4. So, wow, I'm now beginning to think I might be able to solve this. Now, we can actually write some things in, can't we? Because those cells in my 17 cages now are a 1, 2, 3, 4 quadruple. That can't be a 1 or a 2, that can't be a 1. That can't be a 1, that can't be a 1. I've got... now, what else have I got to do now? I've got to put loads of 8s and 9s into my blue squares, because don't forget, the blue squares and the orange squares are equal to one another, not just in terms of the sum, which is what I've calculated, but in terms of their precise digital composition. So, yeah, okay, so the 1s are sort of match, well, 2 of these 1s appear in the 17 cage, so 2 of the blue 1s appear in the 17 cage. Hang on, 1, 2, 3, 4, 5. Oh, that's so clever. That is just beautiful setting. Good grief. Right, let's think back. How many Scrabble tiles are there in my orange bag with a 7 written on them? In fact, we know this exactly. We know this exactly, even though we don't know those squares. We know, because I can't repeat 7 in this, but 7 is in twice for this square, 7's in twice for this, and 7 is in twice for that. There are 6 7s in orange. Well, there are 6 cages in blue that we've not filled in. That's it. We can't repeat 7 in a cage, so every single cage in this puzzle has 1 7 in it. And that is surely important, he says, trying to work out why. The problem is these cages are so weirdly offset, you can't actually deduce much at first blush from that. But we've still got to put in... Right, hang on, let me think about this. We've still got to put in 3 8s and 3 9s into blue as well. This cage, do we know what this cage is? We've got to make 15 in 4 digits without using 7, 8 or 9. I don't know. There's probably some way we can work this out, isn't there? 15 in 4 digits without using a 7, 8 or a 9. Is that restricted at all? I'm not sure it is. I feel like I'm being a bit dense there. Right, come on. How do we make more progress? We're doing quite well. Actually, I'm quite surprised I've only had 29 minutes. It feels like I've been at this longer than that. So I've now dealt with the 7s. I've still got to allocate... Oh, I know what it'll be. Can I put an 8 and a 9 into any of these cages along with a 7? Because there are 6 cages. So maybe I only get to put one of 8 and 9 into all of them. You can't put 8 and 9 in there. You can't. Oh, sorry. I can't put 8 or 9 in there. So now I've got a problem. I've got to put 8 and 9 and 7 into one of these cages. It must be this one. That's the only one that's high enough. 8 and 9 and 7 add up to 24. Ah, I can do that. Good. This is really clever. This is really clever. So because I know I've got 3 Scrabble tiles with 8 in my orange bag and 3 Scrabble tiles with 9 in my orange bag, I've got to put 3 8s and 3 9s into blue. There are 6 cages that I can allocate those 8s and 9s to, but this cage can't have either because it's already got a 7 in it, from the 7's logic. If you put an 8 in here, the other digit would have to be a -1. That means there must be a cage, and there can only be one cage given the options, because there's only one cage that actually adds up to enough, that contains an 8 and a 9. So it's this one. So this has got 7, 8 and 9 in it, and then 2 digits that add up to 5. And every other cage must have an 8 or a 9 in it. Which means that, can I get that? Is there some, I'm just looking at these totals, trying to work out if there's some way of proving what one of them has to be. So if this has an 8 in it, it's 3 7 8. If it has a 9 in it, it's 2 7 9. Sorry, I think I'm making a meal of this now. This cage has a 7 in it but can't have a 1 in it. So it's either 2 5 7 or it's 7 3 4. Yeah. Oh god. Oh no, I don't like this. I still feel like I'm making a meal of it. I've got to put 3 1s in orange. Ah, there we go. Well, there's a small deduction. I've got to put 3 1s in orange. So this cage has a 1 in it. Now, is that important? So now I've got to make 14 in 3 digits without using another 1 or a 7 or an 8 or a 9. So does this have a 2 in it? If it has a 2 in it, that would cancel this 2. That would mean there would be 3 2s in orange, so I have to put 3 2s in blue. That can't have a 2 in it. That can, that can't, that can't. That can. I think this can. And that can. Actually, that's actually very plausible. So we're still not thinking about it quite correctly. That's the royal we. I almost feel like I'm going to have to keep a very precise count on the digits here in order to work this out. So this cage is either 792 or 783. I think if we can get one more cage, the whole thing might topple. We might be able to fill in the jigsaw. Is there a sensible way of thinking about this? I've got to put 2 3s and 2 4s into blue. 3s might be an interesting digit because they can't go in those. I've got to put 2 3s in. Yes. Or at least maybe. 3 can't go in there because it's got a 7 in it. So I've only got 3 cages that can contain a 3. I'd love to know if there's another 3 in there, then I'd have to allocate a 3 to each of these, which would be enormously powerful. 14. Got to put 2 2s at least. I've got 2 2s in orange. Keep going around the houses with this. I've got 2 2s in orange to put in, but I've put 1 in blue already. So I've only got one more 2 to deal with. Got to make 14 here in 3 cells. So there must be a 2 or a 3. If it's a 3, that's the third 3 that I have to allocate 1 3 to each of these. If it's a 2, what if it's a 2 and a 3? It can't be a 2 and a 3, can it? Because then I'd need a 9, which I can't put in there. So it's got 1, there's 1 2 or 1 3 as well. But I could... So does that mean... I'm now starting to think that this one has to have a 2 and a 3 in it. Let me just go through the logic here, and I really apologise. It would be much easier, I think, if I did this not in my head. But I am doing it in my head, and I'm going to carry on doing it in my head. I've got 2 2s to allocate, one of which goes here. So I've now got 1 2 left over. I've got 2 3s to allocate for sure that are not yet placed. And I know that this cage contains 1 2 or 1 3 in order to make up the balance of its total, because if it didn't have a 2 or 3 in it, the other digits would be 4 5 6, and 4 5 6 plus 7 plus 1 is too many. So it has exactly one of 2 or 3. It can't have both, because then it would need a 9. We know it can't have a 9 by Sudoku. So I've either got to put in a second 2 into one of these, as well as 1 2 and 2 3s, or so that would be 2 2s and 2 3s into these cages. How do I do that? 2 2s and 2 3s. That would have to be a 2 3 in there, because I can't put, along with 7, I can't put 2 and 3 into these. So this would have to be a 2 3 pair. If, on the other hand, so this always has a 3 in it. Yeah, because what I was going to say is, if this has a 3 in it instead of a 2, then I've got to put 3 3s in blue, and the net result is the same. I've got to put the 3 3s in those squares, and that happens to mean that the maths of it means that one has a 2 in it. So this cage is a 2 3 7 8 9 triple, quintuple, I should say. I still have to put a 4. Oh, that's it. Oh, you silly man. You silly man. It was easy, and I didn't spot it. But in my defence, I wasn't thinking about the 7 in these 21 cages properly. Because the 21 cage has a 7 in it, it can't have a 4 in it. That's so beautiful. That's just take my hat off beautiful, that is. Because once you realise that, these 17 cages are telling you you've got to put 2 4s into blue. Well, let's work out which cages we could put 2 4s into. Now, you can't put 4 in here, because you can't put 8 and 9 with it, because one of the digits is a 7. Same logic here. You can't put 4 in there, because 4 plus 7 needs another 7. So this has got to have a 4, and that's got to have a 4. And now we know the composition of this cage. It's 7, 4, and 3. We know the composition of this cage. It's 4, 7, and 9. And we still have got... No, we've allocated 2 2s. What have we still got to do? Don't know. So I've allocated both 4s. The 1s at the moment are equal, so that's fine. The 2s at the moment are equal, but we don't know... Oh, the 2s are equal, aren't they? Yeah, the 2s are equal. So, yeah, no, there could be a 2 in here if there's a 2 in there. Oh, gosh. This has to have an 8 or a 9 in it, doesn't it? I still don't think we know which one. Is there another digit that we know must appear in this then? It's got a 2 or a 3. Hang on. I know it's got a 2 or a 3 or not both. Does that mean it has to have 5 and 6? Or have I just been messing about? No, because I don't know about 4. What if there's another 4? That's the key point. Oh, of course. That's the key point again. I keep missing little ways of thinking about this, but I'm slowly getting there. This can't have a 4 in it, can it? And it can't have a 4 in it not because the total couldn't be made, but because if there is another 4 in orange, there is nowhere to put it in blue. So if this has no 4 in it, it must have a 5 and a 6 in it. So this has got, the other digits are 1, 5, 6, 12, 3. That's what we've got in there. So this is now 1, 3, 5, 6 into those squares. I'm just going to triple check the maths because I keep going wrong here. 12, 15, 22. That does work. So now we know that we've got to think about 3s much more seriously. I've only put 2 3s in blue at the moment. I need a third 3. You can't put a third 3 in a 21 cage. There's a 3 in the 18 cage. So that's 3, 7 and 8, which means that's not an 8 or a 3 actually. And that's not a 3. And that means that we've got to put a 5 and a 6 into blue. So what? Oh, okay. So one of these is 6, 7, 8, and one of them is 5, 7, 9. But I don't know if we can tell which way round they go. Okay. Well, let's. I'm not exactly sure how this is going to finish. We know the approximate constituency of these. Maybe I'll write them in. It's either 5, 7, 9, or it's 6 and 8 into the equation. Even knowing all of the digits in orange and blue, which I feel is something of a triumph, even if it's taken me a long time, I'm far from sure this looks a simple way to a simple thing to finish. Can we do anything by Sudoku? That's probably going to be where we've got to look. I've got 3, 4, 7 triple here, so I can remove 3 and 7 from that square, and 3 and 4 from that square. 3, 4, 7. Don't quite see what that's doing. I can remove 7 from... Ah, this is now 2 or 9. 3, 7, 8. Oh, okay. Here's something. 8 in box 3 has to be in that domino. So that's not an 8, that's not an 8, and that's not an 8. Three is in one of those two cells. Oh, that's lovely. Right. God, this puzzle is incredibly good. I will say that. It's frankly genius, this puzzle. This 29 cage has an 8 in it. That 8 must be in one of those 3 cells. So that's not an 8. And now I've ruled out 8 of the whole of that 21 cage. So that 21 cage is 5, 7, 9. I've still got an 8 to allocate. So that must go over there with a 6, 7, 8 triple. Now, does that help us to make more progress? 2, 9. There's definitely an 8 here. So yes, it does. Now, where does 8 go in box 8? It goes in that domino, and that rules it out of those 2 squares, which places another digit at last. We get an 8 here. Now 8 is in this domino, and 8 Oh, 8 here is giving me that digit. That's a nicer digit. That's a 9. That's an 8. That's a 9. That's an 8. That's a 9. That's an 8. Now, is that doing something for me? 9 is now quite restricted in this box. It has to be in this domino. So 9 is not here, and 9 is not here. So 9 is in this domino, which means 9 is not here. And 9 is therefore in this domino in box 3. Yes, that seems to be very important. I just want to check the logic there. I'm not sure that it felt wrong as I was doing it. So I'm I'm old enough, wise enough, and have made enough mistakes that I'm going to check it. So let me think about what I did there. What did I do? I noticed neither of these could be 9. So 9 is in this domino in box 2. That rules 9 out of here, places 9 in this domino. That places 9 in this domino, which is looking at this square, which means I can remove 2 from all of those squares, of course. Okay, maybe that is right then. Also, of course, 9, 9. Which one of these can be 9? Only this square. So that, again, is a little tiny breakthrough, and every tiny breakthrough is very welcome. So, we've now worked out there's... That's not an 8, actually. I've worked that out. 3, 7 pair here. So these squares are 1, 4, 5, and 6. I'm actually going to pencil mark that because I want to try and keep track of everything that's going on. Although that's probably foolish because this is getting so cluttered. That's not a 2 anymore. Is this 2? That's not a 2 anymore. Every digit sort of does do work, but you've really got to be quite careful to see where exactly that work's getting done. 9, no, oh, hang on, 9, 9. There's an 8, 9 pair in this box out of nowhere. That feels important because that means I can work out those 2 squares are a 2, 4 pair. And there's a 2 here. Here we go. 2, 4. So that's not a 4 anymore. There's a 4 in this domino. Oh, I see. So that 2, 4 pair flips and goes in there by geometry, and there's a 2 here. So that's 2, that's 4, that's 1, that's 2. Here we go. Come on. That's not 1 or 4 anymore. And how much more can we get done as a result of that? That felt like a huge breakthrough. Come on. 5, 6, and 9 into these squares, but I don't think I know which way round they go. I definitely know there's a 9 up there. Oh, I've got a 4, 5, 6 triple in this box, so that must be a 1 by Sudoku, which means that isn't a 1 anymore. Where does 1 go in box 4? It's got to go here. 1's got to go here. 1's got to go here. 1's got to go here, and I think we've just suddenly got all the 1s. Oh, I've got a 3, 4 pair here. Let's check that. So I've removed, yes, I have removed 2 from both of those. So that becomes a 2. That becomes a 2 by Sudoku. That becomes a 2 by Sudoku. How strange is this? That becomes a 2 by Sudoku. How many 2s? All the 2s, all the 1s and all the 2s have suddenly got done. Can we do the 3s now? Doubt it, because I don't seem to have got any 3s. Okay, forget 3s. What's this square? Because that square sees 1, 2, 3, 4. That's a 5 or a 6. Bobbins. Okay. I've got an 8, 9 here. Oh, this column, maybe. 6 can come out of that square. 7 can come out of that square. We've got 3, 4, and 5 left to place. I don't believe it. Again, this this escapes and is not under enough pressure. Don't know where to look. Alright, let's have a look at the bottom row. We've got 3s, 5s and 6s to place. Therefore this square also is a 3, 5 or a 6. Okay, here's a nice little thought. Let's come back to our perimeter logic again. This box, where does the 5 go? Answer, don't know, except it's definitely in the top row. Now therefore in this box, where does the 5 go? Definitely in this domino. Therefore in this box, where does it go? Definitely not here, definitely in this domino, looking at that square, which is now a 3. So we can get rid of 3. I've now got a 5, 6 pair here. This 3 is giving me a 4. And that means I've got a 5 at the top now by Sudoku, and a 3, 7 pair here. Don't know. I need a 3, 4 pair to complete this column, so we can write that in. That fixes this square as not a 3. So this square here is just a 5 or a 6. It can't be a 7 or an 8. The question we could ask, of course, is where does 8 go? In this box, it has to go there. I didn't spot that. That was probably an easier way of doing that, but didn't see it. 8 here means this is an 8. So we might be on our road to doing all the 8s now. That's got to be an 8 by Sudoku. No, we're left with a little 8 X-wing in those squares. Okay, what about 9s now? 9s have suddenly got interesting again. 9 comes out of this cell. This square's a 5 or a 6. Don't believe it. Don't believe this column. It's still holding out. Okay, so this square and this square are from a 4, 5, 6. That's not 5. And that one, I don't know. I think it still has options. Okay, let's come back to this box perhaps, where we need 5, 6 and 9. So this square, I keep saying 5 and 6. 5, 6, 9, 5, 6 and 9. So clear. It's so close to being fixed, isn't it? Let's get rid of the 9 pencil mark there. That's bugging me. Get rid of the... No, I'm not going to get rid of the 5s up there. What about that square then? So that square is a 3 or a 6 by Sudoku. And for some reason, that seems to be... that all seems to be possible. Wow, okay. There must be something that's disambiguating the puzzle though. Yes, no, 5 is in this domino. Oh, that's okay. Yeah, okay. Where does 5 go in this box? The answer is in one of 3 positions. 5 in this box is in one of 2 positions. These 2. So where does the 5 go in this row? Answer one of those 2 squares, which means this square is not a 5, and that must be a 6. Oh, whoopsie, I want to get rid of 6 from there. That's a 5, 9 pair now. Oh, I see. So this square should be doable. There's a 3, 4 pair in the row. That's a 7. That fixes the 7 and the 5. The 6 and the 5 get done at the top. That becomes a 6, 4, 5 triple. That's now a 3, 4, 3, 4, 5, 3. Sequence, 7, 8 here. This is a 6. That's a 4. That's a 5. That's a 6. That's a 7. That's a 3. That's a 6. That's a 3. That's a 4. Yeah, okay. I do think we're now on the home stretch. What a puzzle. This is ludicrously clever. Just ludicrously clever. This column needs a 6 and a 3. That's a 3 looking very nice over there. 3 and 6, 6 and 5. Oh, we've got a 7, 8, 9. Hopefully not a deadly pattern. I'll have to figure that out in a minute. 6 here is useful. 6, 5, 5, 9, 9, 7. That's getting us the deadly pattern resolved. West square is a... Where's the 7 in this column? And the 4 I see is giving me that digit. Okay. Oh, suddenly it's done. Suddenly it's done. Wow. Oh my goodness me. Trapped by a killer I certainly was. I'm torn between being utterly delighted to solve that, because that felt impossible for long periods, and a little disappointed with myself because I think I could have really, really streamlined the logic on this central, the sort of making sure my Scrabble bags contain the same things. I think that there were ways of thinking about that would have been far more efficient than the way I did it, which was sort of, continually thinking about the wrong thing. I think the 7th thought to start with was a very sensible one, and that allowed me to allocate 7s all around the shop. But then I didn't focus on 4 for ages, because for some reason in my brain I didn't connect the fact that I couldn't have, because I had a 7 in these 21 cages, I couldn't have a 4. And the 4s at that point were hugely restricted. And, it forced this cage, because you couldn't have a 477 cage in the 18 cage. I mean, the selection of A, the geometry of the cages in this puzzle, and B, the absolute values to allow logic like this to flow, it's sublime. It's incredibly clever. Good Lord, it's incredibly clever. This is one of the, it's one of those puzzles that on Cracking the Cryptic we're fortunate enough to do, once a month or something, but it really takes your breath away when you do it. Let me know in the comments how you get on. I'm going to be fascinated to read whether I've done something clever there by solving it at all, or whether there's going to be comments saying Simon annoyed me because he didn't immediately spot X, Y and Z. So I enjoy the comments, especially when they're kind, and we'll be back later with another edition of Cracking the Cryptic.